So I'm going to start going through chapter 1, FCPure 2, year 13, complex numbers. To begin with, we are going to just have a quick look at the two forms of complex numbers that you should recognize from last year. So the first form is, you could refer to that as a Cartesian form. You could refer to that as a rectangular form also. It's z equals a plus ib. So you break up a complex number into real part and imaginary part, where a is a real part and b is its imaginary part. You can plot that complex number on an Argand diagram. You go a across along what's called the real axis, so that's your horizontal axis, and b up, so as if plotting a point with coordinates a, b on a Cartesian plane. Okay, the second, let me just jot it down. So a is real part, and if you want to write it down, you put re of z, so that's what your a is, and b is going to be imaginary part, and you will call it imaginary part of complex number z is the value of b. Okay, so remember also the definition of I is simply square root of -1. Okay. The second form is modulus-argument form. You can refer to that as a trigonometric form also. So this way you also need to define it in terms of two values. Okay, one goes with the length of the line, or the vector, if you like, that takes you to the position AB. So that is simply called R, which is your modulus. Okay, you also can write it modulus of Z. Okay, and to find out the value of that, you simply use Pythagoras. So a squared plus b squared square rooted. So this would be your length A, and this is length B. There is a right angle. Okay, so you put that value at the start, then you open bracket, and then you put cos theta plus I sine theta. Theta, okay, so if your R is over here, theta is the angle that is gives you the inclination of the point measured from the positive real axis. Okay, so there is your theta. It's given the value of positive in the anti-clockwise direction, negative in the clockwise direction. So theta is what we call the argument of the complex number z. So to work it out, you can just use tan inverse or arc tan of the opposite over adjacent. Okay, but you always plot the points if you want to find the argument and use your common sense. So now I just wanted to mention also, just a reminder, there is what the complex conjugate of our complex number z is the complex number that you will get by reflecting this original complex number in the real axis. So you will get a across and minus b down, so it's minus ib. So if you go, it's somewhere here. Okay, so this is going to be complex number conjugate of the original number a minus ib. Now I've written a over here, and just write it. Now the argument of that complex number is minus theta. Okay, so it's actually a good idea to write down this complex number in terms of its trigonometric form as well. So the look of that number is simply r because the value of r will not change, and then the argument is minus theta, so it's minus theta add I sine minus theta. But although it is in the same form, the better way of putting it, or very often we'll put it in r cos theta, because that is your r cos theta is the value of a minus I sine theta, because the however down you go is going to be equal to however you go up. So if that is r sine theta, then this one is minus r sine theta. Okay, so these two are equivalent, but this is in the trigonometric form. Okay, so we're going to go